Acho que não. Talvez, mas acho que não tô mexendo.
All right. So thank you for coming back from lunch. So here we are, part 4 of labeled Leavitt path algebras. Please.
So today, I want to talk a little bit about partial actions. So Hector already talked about this this week. I think today Thais is also going to talk about the partial actions. And the idea for me is to show how partial actions can be used to model left path algebras and left labeled path algebra as well. And I'm going to explain also some kind of a converse. So given a partial action, try to build a labeled space that gives that partial action. And to start low, the free group will play a very important role in what we're going to do. Just so to explain what we do with the free groups. So the idea is that we have a set A, and we're going to try to build a group in which A is the generator of the group. And the idea, whenever we have these free constructions, we need to, there is always a universal property that I'm not going to write here, but there's a universal property that whenever you have a function from A to a group, you can build homomorphism from the whole free group. But I'm going to give a very concrete description of the free group. So the idea is that, first of all, if the set is the empty set, you just take the free group to be the trivial group. So the interesting example is when the set that generates not empty. And what we do is just we take this set of inverse for the elements of A. So we just denote this by A minus 1. For each element of the original set, we take this inverse. And I don't know, we can try to build this as some kind of a more concrete set. But the idea is that we want that the ladders and the inverses are disjoint sets. And so once you have this, here should be the union. We take the union of these two sets, and we take all the words that we can write with the ladders and the inverse of the ladders. And we include this empty word that I'm going to denote here by omega. So we would like this to be the whole free group. And in fact, we can see that up to some cancellations, it's going to be that. But the easiest way to model out these cancellations is say that whenever I have a word in these ladders, it's going to be reduced. If you know ladder in the alphabet, A is going to be adjacent to its inverse. Because if it's adjacent to its inverse, we can cancel out. So we do this until there is no ladder with the inverse on its side. Whenever this happens, we call this the reduced words. And as a set, we can define the free group as being the set of all reduced words, which includes the empty word, because the empty word has no ladder, so it's going to be also a reduced word. For example, so let's say you have this alphabet with 3 letters, A, B, and C. If you take this element here, have two A's, two inverse of B or inverse of A and C, this element is going to be reduced because even if A has an adjacent A itself and B inverse is adjacent to B inverse itself, there's no ladder that's adjacent to its inverse. On the other hand, if you look at this word, we have that B inverse is adjacent to B, so this is not reduced word. So in this set, this was not going to be in this set. After when we define a multiplication, as I said, can cancel out and see this as a multiplication inside the free group. But let me first explain how do you define this multiplication. Okay, so first of all, the empty word is just the identity of the free group. And what we want to do is that whenever we have two words, we just want to concatenate these two words to be the product. The problem is that when you concatenate two words, it's not necessarily going to be reduced. So we have to cancel out the inverse one of the other. When after you do that, you're going to find a reduced word, and that's going to be a multiplication. So for instance, let's say you have this, again, the same alphabet as before, ABC, have these two words which are in the free group because they are both reduced. When you try to multiply them, what happens? What happens is that if you concatenate X with I just like that, you're going to have B inverse adjacent to B. So you have to cancel out, so you have to simplify this. We do this. When you simplify B with inverse of B, what happens is that A now is going to be adjacent to A inverse. We simplify again. And then you arrive at AC. Now this is a reduced word. So this is the multiplication of X and Y. So we can always do that. Take two reduced words, you put them together, you cancel out all the inverses, you get a reduced word. That's going to be your multiplication in the free group. It's easy to understand how the inverse works. You just take the word you write from right to left, change what's inverse to what's not inverse, and vice versa. And well, it's going to be associative and all that. And as I said, every element in the words, the letters of A inverse can be seen as element of the free group. If you, instead of looking as a concatenation, we look this as a product of the elements of the free group. So after we simplify the multiplication, we're going to find exactly what was the reduced word, but we can always see an element there as an element of the free group. Another other thing that's going to be important for us is that the free group has a length function, which is just, since you have a reduced word, it has a number of letters of this reduced word, so it's going to be a length function of this reduced word. And in particular, if you have the empty word, the empty word has a length 0. Okay, so this is going to play a role in what it's going to do. Okay, so as I said, I want to work with partial action. In order to work with partial action, let's first recall the definition of an action of a group. So we start with a set X and a group G, and here it's going to be a left action, but the idea is you have this map that goes from G times X to X. So we can think that an element of G is acting on this element X is going to take it to this G times X. And you're going to satisfy two properties. One is that we wanted that the identity of the group doesn't change X. So basically, this is going to be this is the identity. And the other thing is that we want to, in a certain way, that the composition or this product here, so if first act H and then act with G, is the same thing as acting with H for NX and J age in the group. But if you want to go for partial action, it's useful to see this group action in a different way. Instead of looking at this map here, we can look at a family of functions from X to X. The idea, well, it's written here, I'm going to show later, but the idea is we can have this family of functions. And these two axioms is just saying that at the identity of the group, this at E is going to be the identity of the map of X. And have this law of composition that mimics this first one, second one there. And then we identify these two approaches just by saying that this function at G, when applied next, is just the product of G next. And we can see that these two, either we give this first, I think the usual definition when we start learning group actions is like the first one, but for partial actions is useful to see as this. we don't need this first axiom if you ask the functions to be already bijection. So sometimes a group action is seen to be a homomorphism from G to the bijection of X. But here I'm just saying this, they are functions. Okay, so we want to generalize this to partial actions. The idea is that instead of our functions being from the whole set X to whole set X, is that we're going to have some subsets of X where the elements of Gx. So let's try to go through to the definition. So again, we're going to have a group G, we're going to have a set X, and then we're going to have a family of, instead of only having functions, we're going to have also a family of subsets indexed by the elements of the group, and the functions also indexed by the elements of the group. And the idea is just this UT is just going to be subset of X, and this collection of functions are going to be bijections between these two subsets. So we always go from T minus 1 to T. So that's going to be the convention that we use. So the first axiom remains the same. The second axiom is just to help us to do the third axiom, that what we really want to do, that when you apply phi of t, then apply phi of s, should be phi of st. The problem is that this does not always make sense, because if you apply phi t of x, it does not need necessarily to be in the domain of phi of x. It does not necessarily make sense to do that. But whenever you have that, you can apply x, phi t on x, and you can apply st on x. This image here, because of the second axiom, is going to be in the domain of phi of s. So this is going to make sense, and it should be equal. So the idea is that we take the definition of a group action as a family of function, we restrict the domains, the codomains of each of the functions, and then it satisfies axioms really close to the definition of an action. I'm going to give examples in a minute. First of all, as I said, I'm going to be interested in partial axioms of the free group. And there are two properties that I'm going to be interested in. The first one is what we call this semi-saturated partial actions. And the idea is that this equality here does not hold always, just hold for this x. But we want this to be always true whenever I have two elements of the free group such that the length of the product is the sum of the lengths. Basically, the idea is that whenever you concatenate this, it's already reduced. So that's the meaning of this equation here. So if you concatenate it's already reduced, then the length of the product is going to be the sum of the lengths of each of these parts. And the second property that I'm going to be interested in is this orthogonality. And the idea is that for the generators of the free group, we want this set UA to be disjoint. So these two things going to play a role in what we're going to do. Okay, whenever we start with partial action, one of the canonical examples is reducing restrict an action of the group to a subset. So let's say you have an action on a set Y, and you have a subset of the set Y, and you want to restrict the action. The problem is that this restriction is not necessarily an action, because we don't know that when we apply eta g to an element of x, is again going to be an element of x. So it's not, we don't know if it's going to be an action unless we know that x is G invariant in the sense that this always holds. But since this is not a hypothesis, we do not necessarily obtain an action. But we can always obtain a partial action when we restrict this. And how we do this is we take this ut to be the element of x that when you apply eta t, it remains in x. So we take this intersection. And then once you do these definitions, we see that we can apply phi t like this, and it's going to be remain in the sets. And so it's one of the basic definitions of examples of partial actions, like a global action and restrict. And a very big problem in partial action is try to go for the globalization. If I have more structure, you want the globalization to have more structure, but I'm not going to talk about this here. And the other example that I want to talk about is the example of graphs, because that's to connect with flat path algebras. We want to try to define a partial action on given a graph. And the partial action, the set where we're gonna act is gonna be the boundary path space that Danie defined, I think, in the first day. And the group that's gonna act is gonna be the free group generated by the edges of the graph. So that's the set, and that's the group. So first thing is that a path is just a sequence of edges. So this sequence of edges can be seen as a word. So it's going to be an element of the free group. And we're going to define a partial action. Here should be F. So we're going to define a partial action of this free group on the boundary path space. It's going to be orthogonal. It's going to be semi-saturated. And the main idea to define its partial action is that the edge of the graph, when seen as an element of the group, is going to act on the boundary path space. The edge is just going to be concatenated at the beginning. And the inverse of E seen in the free group, because in the free group, the elements have inverses, the inverse is just going to cancel out the E from the beginning of a path. The problem is that this is not always well defined, because in order to put E at the beginning, we need to know that we can concatenate the edge of the path. And if the path does not start with E, how can we cancel out E if it's not there? So we need to define these sets in a nice way in order for this to make sense. And we have to define, actually, we need to define set T's for all elements of the free group. So let's go step by step. So first of all, for the empty word, since the identity, it should be the whole set. That's fine. Now, you want, as I said, inverse wants to cancel out what it starts with. We don't only do this for edge, but we can do this for any path of positive length. So take n alpha of positive length. We just take the u alpha to be all paths that start with alpha, which is the cylinder of alpha that then defined in the first day. As for the ones that we can attach b at the beginning, what we need for it to be possible is that the beginning of the mu, so the source of mu, must be the end of beta, so the range of beta, so we can concatenate beta mu is going to make sense. And if we want to do the two things at the same time, want to remove alpha, then we can glue beta at the beginning. What we need is that, first of all, the range of alpha is going to be the source of mu, which is going to be the range of beta. So this condition is going to be automatic whenever we have this range of alpha equal range of the beta. And the second thing that we want is that, because we are defining this for element of the free group, we want that alpha beta minus 1 is already a reduced word, so it's an element in the free group. So whenever we have things like this, we define. And for all other cases, we're just going to say that a UT is going to be the empty set. So more complicated things, because if you want, let's say you want to add, let's say an edge F, and then you want to remove E. Well, we can't remove E because you just attach F at the beginning. So a lot of these multiplications are going to be 0. That's why a lot of the sets going to be empty. Okay, so that's the family of sets that we have for the partial action. We need to understand how the action itself goes. Again, for the empty words, there's going to be the identity, because that's one of the axioms that is needed for partial actions. And the other ones is just saying what we had before. So what's going to be phi of A? Phi of A is going to act on U alpha minus 1. So I'm sorry, phi alpha is going to act here. So it's going to only attach alpha at the beginning. Beta minus 1 is just going to remove beta from the beginning. And then if you take alpha beta minus 1 in this, with the same conditions that I have above, we just remove beta and then attach alpha at the beginning. So it's very natural in a sense. And well, for all other cases, we just have the empty function, and that's going to be a partial action of the graph to for the free group generated by the edges on the graph. Okay, so now I have a partial action. What else we can do with that? We can try to add more structure on the partial action. So for instance, here this boundary trap space actually has a topology, so we can try to consider topological partial actions. And also, then when he was talking about the action of groups, there was a notion of transformation groupoid, and we can also do the same thing here. So we have a transformation groupoid for a partial action, and the idea is the same as before, that gonna have triples that with an element of x on the extremes, and in the middle we're gonna have an element of the group, and once we act t on y, you want this to be x. So y needs to be in the domain of the action for t, and then when you apply phi t on y, you want this to be x. So it's very similar to the transformation groupoid of a group action. We just need more restrictions because of these domains. And the operations are going to be the same. We just triples where the first letter one is the left of the others. So this y must be the same. We just remove the y, multiply the elements of the group, and then we have x and z to be the same. You can see that this actually going to be well defined in the sense that z is going to be in the domain of ts, and when we apply ts on z is going to be equals to x, and the same thing for the inverse. Just writing the other way around. Here should be x, and you have the inverse for the element of the group. And sometimes these triples, we don't need all the information on the triple, just need either the first two parts of the xt or ty, and sometimes it's going to appear in the literature, instead of writing this groupoid as a triple, it's going to be written as a pair. But I think it's easier for us, at least for now, to see this way. Okay, and as I was saying before, we can put more structures on a partial action. So one of the things that we are interested in is using the topology. So we have the notion of topological partial action, and the idea is that we just have a partial action we had before. And here, only going to consider G having the discrete topology. So G is a discrete group, and X is a topological space. And what we ask for it to be a topological partial action is that each set UT, the domains are going to be open. And the other thing that we ask is that instead of only looking at the bijection, we want all of them to be continuous. So the inverse is going to be continuous. So we're going to have homeomorphisms between these open sets. So partial action, when you have topology, we want a little bit more structure from there. And we've put the topology on the transformation groupoid just as being the subspace topology of the product topology on x times g times x. Again, g here has the discrete topology. Then you have a topological groupoid. And in particular, if x is a Stone space, we seen yesterday Stone space just a Hauser space with a base of compact open sets, which is the dual of a Boolean algebra. So if we have a Stone space, then this groupoid is going to be a Hauser-Fumpo groupoid, which we then can try to consider the Steinberg algebra of this groupoid. Before considering the Steinberg algebra, we need to talk a little bit about the algebraic partial action, the cross product. And before that, just to show the example that we just had of the partial action of the pre-group generated by the edges of a graph on the boundary file space. So this is going to be a topological partial action. The groupoid is going to be Hauser and ample. And this graph groupoid actually of the partial action is going to be isomorphic to the graph groupoid that Danie has defined in the first day. And the idea is just to map now for the free group, what is in the middle is an element of the free group. And for what had defined before, what was in the middle was an integer. And the idea is that here I think that here it doesn't depend of beta minimum being reduced or not. But the idea is that we take this middle part and take the element of the free group and just take the length of alpha and minus the length of beta. This is going to be well defined. It's going to be as an isomorph of groupoids. And so after we see how we can define a Steinberg algebra of this in general for these groupoids, we can gonna find an isomorphism between the algebra of this partial action with the Leavitt path algebra. Okay, so that's the topological version of the partial action. Well, let's go for the algebraic version of the partial action. Again, I think Hector already said about this, I think on Tuesday. So when we wanted an algebraic partial action, first of all, here I'm only considering commutative unitary rings. You can do a little bit more general, and then you have an algebra of A. So for the partial action, we want that the domains of the partial action to be ideals. For me, ideal is going to be always two-sided ideals. It starts commutative. Once you have left ideal, you can have a right. Sorry. No. I'm only considering two-sided ideals, and we want this tau t to be isomorphisms for every t. So instead of being bijections, because you have a structure of an algebra, you want them to be homomorphism because they are bijections, they are actual isomorphisms. Okay, so that's the definition of an algebraic partial action, and we want to define an algebra similar to the cross product that Danie defined. I think sometimes we call this skew-group ring, or in the case of partial action, partial group ring, or sometimes it's called a partial cross product or cross product in the case of group action. So I'm because I'm come from sister algebra. In sister algebra, we just use partial cross product. That's the nomenclature that I'm more used to do. So okay, so how do we define this partial cross product? The idea is that first of all, we need a structure for our module, and for our module, we just take the ideals and take the direct sum of the ideals indexed by the group. And usually, there's a delta t here just to indicate where the element here. So an element of this free group is going to be a sum like this, which it should be a finite sum because it's a direct sum here. And this delta t is just to indicate where, in which ideal this element at is. So this is the structure for an R module, but we need to define a product on this R module to be an algebra. How do we do this? So first of all, is just because we wanted the product to be bilinear, it's just enough to show what happens for this alpha s delta s and bt delta t. Here alpha s should be in the ideal ds and bt should be in the ideal dt. So that's enough for us to know what happens here. And the ideal, the first attempt should be just to look at what to do for action groups and try to do the same thing. So we should try to define the product in this fashion. So when you commute delta s of bt, you should apply tau s on bt. The problem is that we don't know if this bt is going to be in the domain of tau s. So in general, this does not make sense. The way that Hector did to correct this was to consider that the ideals are unital, so we could multiply by the unity of the ideal, but I'm not considering the ideals are unital, so I'm going to do this in a different way. How I'm going to fix this? So the first thing we notice that AS is an element of DS, and so we can apply TS minus 1 on this element. And so when we apply TS minus 1 on this AS, this is going to be in the ideal indexed by S minus 1. And so because DS minus 1 is ideal, when you multiply DS minus 1 for AS with BT, now we are in the domain of tau S, so S minus 1. So this element here is going to be in this DS minus 1. And here we can apply tau S. This makes sense. And so we can define the product instead of looking at this first equation. We can just put tau s at the beginning. If this was an action of a global action, we can see that we could cancel out tau s minus 1, just gonna get the as that was above, and it had tau s bt as above. But now this is it always makes sense to do this because of the structure of the ideals. The problem is that this product is not always associative. So there are some conditions that I think this is one of the first main problems of the theories. Try to show that this product is associative. So this because Of course, there are a lot of people studying non-associative algebras, but especially for people that study sister algebras, we want the product to be associative. And one of, I think, the condition that we can give to ensure that this product is associative is to suppose that each ideal is an idempotent, in the sense that every element of the ideal can be written as a sum of products, so you can kind of decompose each element of the ideal as a sum of product of two elements of the ideal. And if this happens, then the product is associative. There are other conditions that also ensure the associativity, but for us, this is going to be enough. Why this is enough? Because the algebra that we're interested in have these local units. So Leah has already talked about local units for Leavitt path algebras. I'm going to give the more general definition here. So let's say you have a ring S and a family of idempotents of S. Say that this family is a family of local units. If you, well, yeah, it acts of a unit, not in the whole S, but in every finite subset of S. There's element of this family F which acts as a unit. So FSI, SIF, it's going to be a psi. For each family, finite family, you can find this element on the family on F. And it is very clear that if you S has local units, it's going to be idempotent because it's written here. You have each element of S. There's a local unit for it, so you can write just the product of these two elements. So every ring which has local units is going to be idempotent. And as I said, for us, the ideal is always going to have local units. And so when you take the cross product, it's going to be associative. Okay, so let's try to go to the direction of trying to define the Steinberg algebra and try to connect with this theory of partial actions. And for that, for the Steinberg algebra, we have a topological groupoid that comes from the topological partial action. In the algebra sense, we need an algebraic partial action. So what we do? First of all, again, we're going to start with just a discrete group, and we want X to be a stone space because we want an ample groupoid, house of ample groupoid. So X is going to be a stone space. And again, we're going to take a topological action. And the difference is that only look at UT asking them to be open. We're also going to ask them to be closed. So this UT is going to be cloping for all T's. And because X has a base of compact open sets, there are a lot of cloping sets. The space is totally disconnected, so there are plenty of compact sets that can be the domain of this UT. And so we're going to try to define an algebraic partial action of the same group in these locally constant functions of this stone space, which we're going to call the dual action of this topological one. How do we do this? So first of all, for each element UT, which is cloping, we're going to define the ideal dt to be locally constant function on this UT. Well, we need to extend actually because we need functions from X to the ring. So the way that we do this is because UT is cloping, we can extend it as being 0 outside the UT. And this is again going to be a locally constant function inside all the space X. And we observe that these DTs are going to have a family of local units, which has this characteristic functions of compact open subsets of UT. So it's going to satisfy the ideals being idempotent, so the cross product is going to be associative. Okay, so we have this set of ideals. Now we need to define the actions themselves. We need them to be algebra isomorphisms. And for people that know operator algebra, this is very familiar, but what we do is just we take a function and then we need to change the t for t inverse. So this phi hat of t, when we apply a function f in the t minus 1, we compose with t phi t minus 1. And it's not very difficult to see because we had a topological partial action that this action that we define here is going to be an algebraic partial action. And as I said, now we have topological action, have on a zone space. So we have an ample house of groupoids. So we can define an algebraic, the Steinberg algebra of this groupoid. If we have an algebraic partial action, so we can form the cross product of this partial action. How do you compare these two things? Well, these two things are isomorphic. So how do you show this isomorphism? It's not really that difficult to show. I'm just gonna give the idea on how the maps work. So first of all, an element on the Steinberg algebra is a function on the transformation groupoid, and we want to find some kind of sum of elements where the function is going to be defined in each ut. And the way that we define this is just take x to be the first element on the of the coordinate in the groupoid. T is going to be the same t as before. And for this to make sense to be in the groupoid, here we apply phi t minus 1. So we can see this is actually, because here is also locally constant function on the groupoid, this is going to, again, be going to locally constant function on ut. And then this map, we have to show that with the convolution product, this map is going to be homomorphic algebras. For the inverse, we do the opposite. And another thing is that because this function has compact support, this sum is going to be finite. Because for since we have the G has the discrete topology at most for a finite amount of t's, this functionality is going to be different for 0. And for the inverse, we take this sum, and then now we define a function on the transformation groupoid, which is basically do this the inverse what we had before. So we have the triple here. We just define this to be ft of x. And then we again can well, actually don't need to show that it's an homomorphism, because once we have the first one is a homomorphism and it's a bijection, so this inverse is also going to be homomorphism. So this is going to give us the isomorphism between the Steinberg algebra and the partial cross product. I don't think I've written the example of the graph here, but let's say this transformation groupoid, y is the transformation groupoid of the partial action of a graph. Then Danie has shown that the algebra, the Steinberg algebra of the transformation of the graph groupoid is the algebra of the Leavitt path algebra. And because the transformation groupoid is isomorphic to the graph groupoid, we also get the left path algebra is a partial cross product. I'm going to talk a little bit about the left label path algebra case, but since I didn't go into the details yesterday, I was also going to go into the details here as well. But we can do the same thing. So I went a little bit fast yesterday, but the idea is that if you have a label space, instead of we can build this kind of a topological graph, which we call a topological correspondence. And the idea is that the edges is going to be different for the range in the source map. I don't want to go into details here. And we have this E1 as being disjoint unions of elements of topological space associated with a ladder here. The ladders are the labels that are in the label space. So there's a construction here that we can define as a topological. We can define this as sometimes it's called a partial topological graph or topological correspondence, and then we can define a boundary path space as we defined before. So there's a topological space that we're gonna work with when we define this partial action. And the idea is that these elements of E1, they are going to be indexed by A, because here is a joint union. But also there's an element of XA. XA is the dual of a Boolean algebra, so this F here is just to represent a filter. So each element of E1 is going to be indexed by ladders and filters. And we have when we have a path, we're going to have a sequence of ladders and a sequence of filters. So as I said, it's a little bit more complicated, but the idea is somewhat similar to graphs. So how do we define the partial action? as before, in the identity of the free group is going to be everything. For this alpha, we need to start with alpha, but now because we have these filters playing a role, we need not only the alpha, the path alpha, but we need the sequence of filters. But the sequence of filters can be anything. We just look at the letters above. There's a condition similar to what we had before. How can you connect certain path beta at the front? The same thing for u alpha beta minus 1. And for all other cases, it's going to be empty. A little bit more details, but it's very similar to what we had to grasp before. And here I wanted to remark that, well, we don't have the topology, but all these UTs are going to be compact open subsets. Not only cloping, but they're going to be compact open. It's going to be important when we're going to go to the converse of this construction. Okay, so how do we define now the partial action? Removing ladders is easy. We just see if the path starts with this label alpha at the top, we just remove it. But to define the inverse, it's very technical, so I won't go through the details here. This description is much more technical. But there is an inverse, this is an homomorphism. So in order to define the partial action, once you know this inverse, we can define phi alpha as being the inverse of this alpha inverse. And for decomposition, if this is a reducing word because we want a semi-saturated partial action, we just take this composition. And with this construction, the topological partial action gives us a transformation groupoid. There's a groupoid that they are in the slides yesterday for those who are interested to look at later. But the idea is that this transformation groupoid is going to be isomorphic to the groupoid I described yesterday, or more precisely, they had described in the slides for yesterday's talk. And because of the results that we have, so this left label path algebra is the Steinberg algebra of that groupoid. So it's going to be the Steinberg algebra of the transformation groupoid, and the Steinberg algebra of the transformation groupoid is the partial cross product of this dual partial action. Okay, so not only left path algebras, but these left label path algebras can also be described as partial cross products. Now I want to do the converse. I want to show that in certain conditions, partial cross products can be described using labeled spaces. And first of all, I'm going to do this for topological partial actions, and then I'll go as a corollary to the algebraic partial action. So what do we need as an input? First, we take the X to be a Stone space because we need a Boolean algebra for the label space. We have this partial action. It's going to be semi-saturated and orthogonal. And we want this VT to be compact open because for the label space, they are compact open. So we ask this as a hypothesis as well. And then we can build a label space in such a way that there's a homomorphism between the Stone space that start with and then the boundary pair space of this label space that I described yesterday, or as I said, it's described there in the slides. And this homomorphism is going to be equivalent with respect of the partial action of the free group. And because this is equivalent, this is going to give us an isomorphism of the topological groupoids. So, as I said, so every action of the free group with the same saturated orthogonal with this condition of the domains being compact open is described by the labeled space. And how do we build this? Just so we have an idea. So first of all, we need the labels. The label is going to be the generators of the free group. We need the edges. The edge is going to be the set X itself. We're going to forget the topology for now because the topology is going to appear again when we talk about the Boolean algebra. And then we need the edges. So the edges is going to be these pairs AX, where X it belongs to VA there in the partial action. And we need source and range map for these edges. So the source is just gonna be X itself. And for the range, once we know that X is in VA, we can apply the action of A minus 1 on X. So this is gonna be the range. And the label is right there in the pair, so the label is just A. And we need a family of a Boolean algebra going to satisfy all the needed definitions, and the Boolean algebra is just going to be the compact open subset of the stone space. Then there's a lot of work to do to show that this topological space that we find here is going to be isomorphic to the X itself, and the isomorphism that we obtain is equivariant with respect to the partial action, so that we have the same groupoid that we had before. And we could do the same thing now for the algebraic setting. In the algebraic setting, what we need commutative algebra, because we saw yesterday that we have commutative algebra that generated by idempotent, which is torsion-free. You don't need torsion-free, you just need torsion-free on the idempotents. But then this algebra A is going to be described by a stone space. And we need a partial action of the free group on this algebra in such a way that these ideals are unital, because we are asking in the previous theorem that the sets are compact open, being compact being that the algebra is unital. So we ask these two to be unital, and then we can find a label space in such a way that this partial cross product is exactly left labeled space, or the left labeled path algebra of the label space. So how do we do this? As I said, because of these hypotheses on the algebra A is a locally constant function on a certain stone space, and each ideal is going to be a locally constant function on some compact open subset for T, not the empty word, because these are unital. UT is going to be compact. And then we can define a partial action on using the algebraic partial action, because we have kind of a duality. I just explained from the topological how to go to the algebraic, but from the algebraic we can also go to a topological partial action, because isomorphism or homomorphism between algebras, they preserve idempotent, so they're going to preserve the Boolean algebras, and we're going to take the duality, or stone duality. And then as a consequence of the theorem before, is that we get this algebraic partial action is going to be isomorphic to the partial action on this locally constant function, which by the theorem, all the theorems that we had before, is going to be isomorphic to this left labeled path algebra. So we have these very large classes, suppose that of partial action that can be described using labeled space. And that was it that I want to talk today. Just a few references. So, well, there's now the book by UFSC on partial actions. There are a lot of stuff there, not only the algebraic version, but the sister algebraic version as well. There's this paper by Viviane and Danielle, where they study this description between Steinberg algebras and partial cross products. And well, this is the same as again before. And this we just put this week, because this definition of the partial action label space that I gave you is not the same that appear in our paper. In our paper, we go in a different approach. So there is this notion of well, you can construct a groupoid from an inverse same group, and then we use the inverse same group there. But I think the description here is more complicated, and we simplify a little bit in this paper, and not only for labeled graphs, but we've done this for the generalized Boolean dynamical system. Okay, so thank you for your attention.
Questions, comments? Gilles, can you go back there? There's one or two slides. So the corollary here, so we had the result that when R is commutative, A is torsion-free commutative, then it can be seen as a as the algebra of the label Leavitt.
Yes.
Is that so? If it was a sister algebra, that would be C0 of x.
Yes.
And was that no? I don't think did we write that? No, right?
We didn't write that, but I've written that for the Boolean dynamical system in the sister algebra setting.
Okay.
In the Boolean dynamical system, we can remove this hypothesis that these are unital. There is an hypothesis extra in the topological version for Boolean dynamical system. Instead of looking at compact open, we can remove this. And just for the degenerates of the group, we ask the set to be cloping. So it's a little bit weaker, but then instead of looking at this labeled space, you have this Boolean dynamical systems. But then yes, then we don't this in the sister algebra setting as well.
Okay. Any more questions?
So just for tomorrow, we're gonna have a training session. We prepare some exercise to work on here tomorrow. I'm gonna send to Daniel for him to send for everyone to have.
Luis.
Oh, Luis.
Luis.
Is Luis here?
No, but you can send to him. He's the one in charge of that.
Oh, I tried to today. I think he went to Spain, but anyway, we're gonna have a training section tomorrow. The idea for tomorrow is trying to instead of giving a lecture here, is try to work a little bit of the details. So we separate two things to do. The first one is just looking at the Steinberg algebra of the graph groupoid and really showing that it satisfies the relation that Leah gave, this V, E1, E2, and the CK1, CK2. And the other exercise is looking at a more of a dynamical point of view, that the relation satisfying in the left-graph algebra can be interpreted in a more dynamical way. Well, it's written there. We're gonna try to send you this today, so that tomorrow we're gonna work this here.
Okay, perfect. Thank you. So let's thank Gilles once more. And we take a 10-minute break, and then Thaisa is gonna talk.